Alright, today we're going to take a look at how to draw Lewis structures. And Lewis structures are a representation of how electrons come together from single atoms and are joined together to form molecules. So these are representing covalently bonded molecules, meaning that there are two or more pairs of electrons being shared between two or more atoms. So first off, let's just take a real quick look at a Lewis dot diagram. Those are very simple structures for individual atoms of elements. So for example, if I look at iodine, which is in group 7A, which is a halogen, has 7 valence electrons, I would write the symbol, and then since it has 7 valence electrons, I would draw 7 dots. And notice that I can put up to 2 dots per side, and there's pretty much 4 sides. You can kind of imagine it in an imaginary box. Whoop. A little too far, and there's the Lewis dot diagram for iodine. Now the idea with the Lewis structure is that if I have, well, we know iodine is one of these diatomic molecules, so if I imagine another iodine atom and draw its Lewis dot diagram, oops, with 7 electrons, we can see that when these two atoms approach each other, since they both need just one more electron, we can see how these two will come together and actually end up forming a molecule. So instead of drawing the 2 dots in between the iodines, we're actually going to draw that as a dashed line connecting it. So this is representing those same 2 electrons, and then we will have the other pairs of electrons that are non-bonding. So we'll call those non-bonding pairs. You can call them unshared pairs. Anything along those lines. We may refer to those unbonding electrons that belong just to one type of atom. And there we go. There are our Lewis structure. There's our Lewis structure for I2. So again, that's one of our diatomics. So again, this is a stable structure. The thing that we know about the way molecules, the way atoms combine in molecules, is that in a lot of cases, atoms, or at least atoms of the main group elements, tend to come together in a way to form 8 electrons around each atom participating in the compound. So we call that the octet rule. You'll notice that there are, if we just count up here, we've got 2 plus 2 plus 2, so that's 6, plus these 2, that's 8. So these 8 electrons are in contact with this iodine atom. Again, these 3 pairs are not bonding with any other atom, so those are lone pairs or unshared pairs that belong just to this iodine atom. And then we've got this shared pair that also counts towards this iodine atom's count, and so that's a total of 8 as well for that iodine atom. So both have 8 by participating in this bond. And so that's really going to be our guiding principle for how to figure out when our Lewis structures are complete. The other thing we're going to look for our Lewis structures to be complete is the correct total number of electrons. So again, if I know that this has 7 electrons and this has 7, that adds up to be a total of 14. So my structure, to be correct, has to show these 2 atoms both with 8 electrons around them, but only a total of 14 electrons. So that's going to be our objective here. So let's take a look at another example. And right here. Okay, so let's look at PCl3. PCl3. So phosphorus trichloride. And so first thing we can do is count up the numbers of electrons that are going to appear in the structure. So we've got 5, because phosphorus is from group 5A, and chlorine has 7, but there are 3 of them, so we would factor that in. So there's going to be 3 chlorines coming in with 7 electrons apiece, and so that's going to add up all to 26 electrons. So our diagram is going to have 26 electrons in it to be completely correct. Okay, so next thing we need to do is pick the central atom, and in the last example we saw there was no central atom because there were only 2 atoms, but if I have more than 2, like in this example, then I need to pick something to go in the middle. So it's going to be the least electronegative element goes in the middle. The only exception to that is going to be if we have hydrogen, and hydrogen is never ever going to be in the middle, so that's very important to keep in mind. So Typically the way these formulas are written is the least electronegative element is actually usually written first. You can also look up the values, or you can look at the trends in the periodic table to try to figure that out. But we know that phosphorus is to the left of chlorine in the table, so that would make sense that it's the least electronegative, and that's going to go in the center. First step is to always connect all of these other atoms. So we've got 3 chlorines that need to be attached. Those are all going to be attached to our central atom, and we're going to refer to the chlorines as terminal atoms, meaning they're at the ends. Okay, so each of these red lines that I've put in here, those are single bonds that are showing, so that's a pair of shared electrons between the phosphorus and the chlorine. Okay, so I've got 26 electrons to show. Right now I have 6 shown, so there's 2 more, and there's 2 more, so that's a total of 6 electrons that I have already drawn, and so that means that I need to show 20 more. So you're always going to start with distributing the amount of electrons that you have to distribute over the terminal atoms first. So I'm going to start with this one on the left, just because that's how I like to start. So I'm going to give this one, this chlorine, 3 more pairs, so that's going to give it a total of 8, because this counts towards chlorine's total, and then these ones that I just drew in also count towards chlorine's total, so that gives chlorine 8, and I'm going to keep going around doing the same thing. Notice that I'm drawing dashes instead of the dots around the chlorines, and again, as long as I'm laying them flat against the chlorine, what that means is, like, I wouldn't put the pairs sticking out like this, because that would imply that they're going to be bonded to somebody, but the fact that I have them laying flat against the side, right, so laying like that, that means that that's a non-bonding pair. So you could do the dots if you prefer, you can do the dashes. Sometimes with these L's it makes it a little bit harder to use the dashes, but anyway, so I've gone around each of the terminal atoms, and you can see I've got 8 electrons around each. Again, the bonding pairs are counting towards that total for the chlorine. And right now, if I count up how many electrons are shown, I have a total of 24. So if you count up all the pairs, that's a total of 24. So I've got 26 left. Notice that phosphorus only has these 3 pairs already, so that's 6 electrons. So phosphorus still needs 2 more to be 8, to have 8, and there we go. So now my structure, if I double count, I do have 26 26 total electrons, and every atom has 8 electrons around it. So again, I can circle, and you can see that again, any shared electrons count towards the total of the each atom that they're being shared between. But again, in my total, it only counts once. And so there's the structure for phosphorus trichloride, again without the circles around them. That would be what it looks like. Okay, let's take a look at another example where we've got some exceptions. Let's look at the hydronium ion, which, if you remember, is what we see when we're talking about acids and bases, and that's H3O+. If you happen to have something that has a charge indicated on the formula, you do need to account for that in your electron count. So when we're counting up the numbers of electrons, we will factor that in. So I've got each hydrogen has 1 electron, and I know that there's 3 of them, so I need to factor that in. And then I've got 1 oxygen, which has 6 electrons, and then the positive charge, what that means is this group as a whole has, and with a positive charge, that means a loss of 1 electron, or for a +1 charge, it'd be a loss of 1 electron. If it was a +2 charge, it'd be a loss of 2 electrons, and so forth. Likewise, for a negatively charged ion, it would be 1 electron gained for a -1, or 2 electrons gained for a -2, and so forth. So I'm going to subtract off 1 from my total for the numbers of electrons. So this is going to be 3 plus 6 minus 1, and that is going to be 8 electrons that need to go in my drawing. So we are going to just start putting everything together. I did say the least electronegative element should go in the center, and when we look at this molecule, we've got H and O, and we know that H is a lot lower in electronegativity than oxygen. However, we also said that hydrogen cannot ever go in the middle, and the reason for that is this is one of our exceptions to the octet rule. It only takes up to 2 electrons, and the reason for that is if you think about hydrogen, its electron configuration is 1s1. The first energy level actually only holds up to 2 electrons, and so once hydrogen is bonded to another element, it will have a total of 2 electrons to its name, right, because it's sharing a pair then of electrons, and that's satisfied, just like helium is satisfied with only 2 electrons, even though it's, it's a noble gas, and it does have a complete outer shell of electrons, but that happens to be fulfilled with only 2. So hydrogen's the same deal, so it can only get 2. So that's not going to go in the middle. So we'll put oxygen in the middle because that's the only other option here. So there's the O. And then with single bonds, we're going to attach all of our terminal atoms. And again, with the hydrogen, once it has one single bond attaching to the central atom, that's it. It is not going to have any additional electrons assigned to it. So that means that I've got 2, 4, 6 over here. And so that means that the only other place that we need 2 more electrons is on the oxygen, and there it goes. Now the other thing that we need to mind is if we factored in this charge when we were figuring out the number of electrons to represent, we also need to indicate why does this drawing, which has 3 H's and 1 O, why doesn't that have 9 electrons? And so we do need to indicate where that electron count came from, and so since that formula had a charge on it, we need to indicate the charge on the structure that we drew. So you put the whole thing inside brackets and then put a plus sign outside. And so there is looking at how do we draw, and this is a polyatomic ion. It happens to be held together by covalent bonds, but that's how you would draw the something with a charge. So just have a change in the electrons. We also need to show the charge on the structure, and that's also one of our exceptions to the octet rule, the most common one we're going to see, which involves hydrogen. Okay, the next thing we're going to take a look at is the possibility of more than one way to do a correct Lewis structure. And so if we have something like, let's see here, let's do CO2. So this is carbon dioxide. And when we look at carbon dioxide, we can look at the total numbers of electrons. So we'll add that up. And so there's 6 for that, times 2. And so that's going to add up to 12 plus 4. That's 16 electrons that need to be represented. Carbon's the least electronegative element, so that's going to go in the center. And then we've got single bonds to oxygen to start us off. All right, next thing we're going to do is start distributing our electrons. And so if I am starting to distribute my electrons around the O's, I'll give this one a complete octet, give this one a complete octet, and you'll notice then I've got 2, 4, 6, 8, 10, 12, 14, 16. I have 16 electrons shown. Great, that's what we need. However, carbon actually only has 4 electrons shown, and so that's not good enough. Now, if we run into the problem where we don't have enough electrons to give every element a complete octet that needs one and still have single bonds, that's when we need to introduce the idea of double or triple bonds. So a double bond is basically taking, one of these pairs of electrons that oxygen has all to itself. Instead of that belonging just to oxygen, if we move it over so that that pair is also shared between oxygen and carbon, what that leaves us with is a double bond here. Notice my electron count has not changed because I just moved one of these pairs that was over here over to here. So I haven't changed my total electron count. And so if I was short just 2 electrons, doing one double bond would accommodate me. But in this case, since I have still another 2 electrons that I'm short, carbon still needs 2 more electrons, I can do the same thing over on the other side here. So I'm just going to move this pair of electrons over to be shared between oxygen and carbon, because that oxygen atom doesn't need to have those 3 pairs all to itself. So there we go. So we double check our structure. We've got 2, 4, 6, 8, 10, 12, 14, 16 electrons total. And we've got 8 electrons for each element. And there we go. Now, another thing when we're looking at, is there another way to do this? One of the things that's good to factor in is what's called a formal charge. And how we look at, or how we calculate a formal charge, is to look at the number of valence electrons an atom comes to the table with. So just looking at oxygen, for example, it has 6 valence electrons normally to itself. And if I count up how many electrons it's been assigned in this structure, that's what I'm going to subtract off from this value to figure out the formal charge. So this is the number of valence electrons that it came in with. And so notice that oxygen has 2 plus 2, so that's 4. And then for any bonding electrons, again, this is 4 electrons that are being shared between the oxygen and carbon, but we're going to count half of those, right, because it's being shared. So instead of counting 4, we'll count half the bonded number of electrons, which would be 2. So we've got 2 plus 2, that's 4, plus 2 more, right, half of the bonded number of electrons, so that's 6. So the formal charge would be the number of valence electrons that carbon originally had, minus the number of electrons that are assigned to oxygen in the compound, and that leaves me with a formal charge of 0. So the objective here is that we can check our structures, and so this is going to be a formal charge of 0 for the oxygen. So typically the structure that's most likely to really be what exists in reality is the one that's going to have the least number of formal charges on the atom, so having 0 is good. Obviously, if we notice the oxygen on the other side is exactly the same setup, that's going to be a formal charge of 0 as well. The carbon, let's check that out. So carbon comes in with 4 valence electrons, and then we count, again, there's no non-bonding pairs around carbon, so we're looking at, there's 4 electrons being shared plus 4 more, so that's a total of 8 being shared. So we do the plus 1/2 the total number of electrons being shared. That's another way of writing out what we did over here with the 6. And so that comes down to a formal charge of 0 as well. Now, if I wanted to look at other ways to draw this with 16 electrons and still have a complete octet for everyone, I'm just going to make some space up here. And notice that instead of me forming 2 double bonds, what I could have actually done was put the carbon in the center, put the oxygen over here with 3 unshared pairs, and then I could have done a triple bond with the oxygen over here, because notice this structure also gives me a total of 16 electrons and a complete octet for everyone. Now, if I go to look at what's the probability of this structure versus the structure with the 2 double bonds, we count up the formal charges and compare. Again, oxygen comes in with 6 electrons, and then we are subtracting off, well, here we've got a non-bonding pair, so that's 2 electrons. We'll put this in parentheses, plus, again, we're going to do half of a bonding number of electrons. So I've got 6 electrons bonded here, so that's going to be times 6, and so that means that I've got, so this is going to be a 3, so 6 minus 2 plus 3, so that's a plus 1 formal charge on the oxygen this time. And for the carbon, we are going to have a formal charge of, well, same thing as the last time, so that's going to be in the, we still have 8 electrons bonded. There's a 4 valence electrons that carbon came in with, and so minus half the bonding number, and so that comes out to a formal charge of 0 for that. And for this oxygen, we've got, let's see here, oxygen comes in with 6 valence electrons minus, and we've got 3 pairs of non-bonding electrons, so that's 6 electrons that are not bonding, plus we've got 1 pair that is bonding, right, so that's half of that goes towards that, so that's 6 minus 7, and so that's going to be a negative 1 formal charge on oxygen. So notice that this structure, even though it's possible to draw it, what the formal charge calculation shows us is that it's unlikely to actually be in that state. And actually carbon dioxide is pretty well studied, and we do know that carbon dioxide actually has two double bonds instead of the one single bond and one triple bond. So this is our structure that we're going to stick with. So we want to draw the structure that has the, if there's more than one way to do it with the correct, correct number of electrons and the correct octet for everybody, then looking at formal charge to figure out, well, what's the most likely structure. It's going to be the one with the fewest number of atoms with formal charge, and also, if there's going to be a formal charge, it's best to have a negative formal charge on the most electronegative elements. So those are the key things to keep in mind. So, fewest formal charges, period, but also if we have to have some having the most electronegative element with the negative formal charge, that's what structure is most likely to be in existence.